All right, well, welcome back. So, last time we talked about single lenses. Today we're going to talk about multiple lenses and combinations. Turns out once you understand single lenses, you can handle multiple lenses. It's just a little bit more of a tedious process. What this gets us into is the world of optical instruments, things like telescopes and microscopes. On the way there, we'll take a detour through magnifying glasses to see how they work, because it turns out you need to understand magnifying glasses in order to understand how telescopes and microscopes function. Well, let's start, as we usually do, with a question. So you may have seen pictures like this. Often when somebody takes a photo or a movie where there's a bright object there, possibly the sun, you're going to see these artifacts, these sometimes polygons or circles or all this stuff kind of emanating from that bright object. It's called lens flare, and the question is, what increases your chances of actually seeing this if you take a photo or if you take a movie? So which of the following 5 things would actually increase the chances of seeing lens flare? Think about that a little bit. Pause the lecture, go to the quiz, give your opinion, and then come back and we will talk about it. Okay. First off, I have to note this. I think this is pretty interesting. Probably 1 in a million. It'll never happen in the history of humankind again, but oh well. So what will actually increase your chances of getting any kind of lens flare? Turns out lens flare is caused by multiple lens systems, by having composite lenses that are formed by lots of different lenses stacked up. Now, before we get into that, there's one really interesting thing that I've noticed. Maybe you've noticed it too. If you've seen any kind of animation, or sometimes animation in video games will do this, often they'll recreate lens flare. Often if you see a picture of the sun or a bright light, they'll recreate all of these polygons and circles and artifacts emanating from that bright light. Turns out, you only get that with a camera lens. Like modern day camera lenses are actually quite complicated. You would not get that if you don't have a camera, which is the case with animation. I mean, you're drawing the picture, there's no camera there. There's a way in which people, maybe in the West, have become so used to seeing through the camera lens that we replicate those effects even when we don't need to make it look authentic. I think that's interesting. Okay, it's a deeper question, it's philosophical, whatever, but interesting nonetheless. So here is a picture of a kind of composite lens, all these different lenses stacked up, and at every interface we're going to have the opportunity for both reflection and refraction. That creates the possibility of stray light somewhere in the system. Sometimes things are going to reflect when you want them to refract, or at least a portion will reflect. Remember, when light is incident on the surface, almost all the time, except when there's total internal reflection, you're going to get both reflection and refraction. That creates these stray rays that come out as a lens flare. So lens flare is really a product of multiple lens systems' modern camera techniques. All right, let's move on. So how do you handle multiple lens systems? Well, it turns out the way you do that is by taking one lens at a time. There's really no way to leap ahead. There's no way to, in one swift move, get through multiple lenses and figure out, well, what's the image created by this group of lenses? You have to go one lens at a time. So for instance, in this situation, we've got 2 lenses. We have our first lens, which is a diverging lens. We'll call that lens number 1. We have our second lens, which is a converging lens. We'll call that lens number 2. And we have the focal lengths of both of these lenses up here. Focal length of the diverging lens is negative. That's really important, and we have to preserve that negative sign whenever we do any work with the lens equation. We also have some information about the relationship of these lenses to each other. So for instance, we know the distance between them. That's usually given as L. We know that's 2 centimeters. And we know the initial object distance between the object and the first lens. So that's what those subscripts mean. We will at some point talk about an object distance between an object, which will be the image created by the first lens. That might be confusing now, but I hope you'll understand in a second. And the second lens, we're going to call that DO2. But we'll get to that. Okay, so what we have to do in this situation is just go one lens at a time. So we're going to ignore the existence of lens number 2. I'm going to pretend like lens number 2 does not exist. It's not there. I'm going to blank it out of my vision. I'm only going to worry about lens number 1. Because that's all the tools I have. I can just deal with one lens at a time. All right, so we're going to do our ray diagram for lens number 1, and then we're going to do a ray diagram for lens number 2 using the image that lens number 1 creates as our object for lens number 2. Okay, here's what I'd like you to do. Probably good if you printed this out, if you're able to. You could look at the previous slides, or this should be on the handout. I'll try to make sure it's on the handout. It's also on the quiz question that you're going to need to answer. The question is, what is the image created of this object by both of these lenses together? We've got multiple different options. Now, this is not a particularly easy question because it does require these 2 steps. So I would encourage you, take a little time with this, use a ruler, try to do a careful job, and figure out which of these images is the image that both lenses together create of our initial object, and go one lens at a time. So pause the video, get your ruler and your pencil, and give a shot at this, and then go to the quiz and say which of these images do you think is the correct one. Okay. Well, let's give this a shot. Now, because it is difficult to draw these lines on an iPad, I did animate this out. It's also, these multiple lens systems can become somewhat clogged with lines, so I just wanted to make sure it can be a little messy drawing with the iPad, so animating this out makes things a little bit cleaner. So here we go. I'm just take that first lens, ignore the existence of the second lens. I don't care about it right now. I'm just interested in that first lens and what image it will create. Okay, first ray coming horizontally along the principal axis, parallel to the principal axis for this first diverging lens. When it hits the lens, it will be bent away from the principal axis as if it came from the focal point on the side of the lens the object's on. So I'm going to get a ray that's diverged up and away from the principal axis like this, as if it came from this focal point here. Okay, first ray down. Second ray goes through the middle of the lens. Nice easy ray, doesn't get deflected at all. I can actually see where my object's going to be. It's going to be right there, where those 2 rays cross, the one that actually does pass through the center of the lens and the one I project backwards. Now, I don't need to, but I am going to draw a third ray, just so I have it. This is the one that will be heading for the focal point on the far side of the diverging lens. So that's how we handle this ray for diverging lens. It's heading for the focal point on the far side. Doesn't quite get there because it intercepts the lens first. What the lens is going to do is straighten it out, and so it will become parallel to the principal axis. This is the reverse of the first ray we drew. It's just something coming in parallel gets bent up and away, something up and away gets bent parallel. Remember, we can reverse the arrows on ray diagrams anytime we want. If I backtrack this portion of the ray here, it's just going to confirm for me that my image is located where I think it is. So this is the image created by the first lens. And let me actually erase a little bit so we can see more clearly here. This red arrow is the image created by the first lens. Now, I am going to use that as the object for the second lens. The second lens sees this as its object. All of the rays that hit that second lens are coming from the first one. If we were looking through that first lens, we would see what appears to be that red arrow. That's the point of an image. The lens creates that image for us, that optical illusion. We're going to fall for the optical illusion, so is lens number 2. So when I start to draw lines, my object now becomes the image of the first lens. So far, so good. So let me start to do that. I'm going to take a ray that heads from this object in quotes. I'm doing air quotes. You can't see that, but that's what I'm doing. This image the first lens creates, my object now for the second lens, there's a ray that comes out of that and heads through the center of that second lens. Does this ray actually exist? No. From this point on, it sure does. But backwards, it doesn't. It's not a real ray. It's something that passes through the diverging lenses and is deflected somehow. But as far as lens number 2 knows, this is just like your eye. This is a legitimate ray. All right, next ray, coming straight in. This is actually something I drew before. Again, this part of the ray actually does exist. The other part is something I backtracked, but that's only to say it looks as if the ray is coming from the tip of this arrow to lens number 2. So I'm going to replace that by a green ray, hitting lens number 2. Now anything coming in parallel to the principal axis for a converging lens, it will be deflected down through the focal point. I can kind of see what the answer is. Usually can't after 2 rays, but we'll keep going just for the sake of it. Third ray now from this new object, again air quotes. I'm going to have something that goes through, here is the focal point of the converging lens on the same side as the object. I'm going to send something through there that is going to be straightened out so that it is parallel to the principal axis. It's, again, the reverse of the ray that comes in parallel and is deflected through the focal point. This is through the focal point and then goes out parallel. Again, everything ends up at E. So the final image created by both lenses is going to be E here. All right. Now, I can ask about magnification. Magnification, we really can't use ray diagrams to precisely pin down. It's something that we really need to use equations for. So, if I want to know what is the final magnification of the object, I'm going to need to do a little bit of math. Rather than ask you to do it, I will show it to you here. Here are the calculations required to get the final magnification of the image, which will be a product of the magnification introduced by the first lens and of the second lens. I take the product of those two things. That then is the total magnification of the system. If I had a third lens, I would multiply by a third lens. So if the first lens increases the lateral size by 2, and the second one increases it by 3, the total would be an increase by 6, 3 times 2. Not quite so simple here, but the idea is the same. So in order to get the magnification for the first lens, I'm going to need both the initial object distance and the image distance for the first lens. Same for the second lens. Now, what this is telling us is a magnification of minus 4.9. The minus means it's an inverted image, so far so good, but it's also telling us it's roughly 5 times as large as the object. That's not true. That final image is not 5 times as large as the object. Well, you got me. This is not the correct answer. There's an error somewhere here. There's a mistake. So what I'd like you to do is look at this, and this slide is actually on the quiz. You can examine it, examine the steps, and try to find where the error is. At which point, A, B, C, D, E, was the error made. So pause the lecture, go to the quiz, examine this process, and determine at which step was the initial error made. Okay. So let's go through this a little bit. So step A, we are finding the image distance for that first lens. And we're using this handy equation that I've given you on a couple of occasions already. Well, we know the initial object distance, plug that in. We know the focal length of the first lens, plug that in, put the same numbers down here, and we get this. So far seems okay. We can check it. So what do we know? We know that this negative says that it is a virtual image. So if we have a distance that is negative, it means that it is a virtual image. And this is about half the distance of the initial object distance. So let's just take a quick look. Yeah, so it is a virtual image. It's on the same side of the lens as the object here. And it's roughly half the size. Or half the distance, sorry. Half the distance between the lens and the image as between the object and the lens. That's roughly half. Okay, I'm willing to give that a pass. So A looks okay. What about B? Well, I want to know what is the magnification introduced by that first lens. I take my image distance. I have to have a negative here. All these numbers look okay. And the image does seem to be roughly half the size as the object. So here I've got roughly half the size. Okay, and sorry for these multiple animations that happen here. So A and B both look good. C, excuse me. Now we're going to take the object distance for the second lens times the focal length of the second lens. Well, now we've plugged in the image distance I get here, my 1.64. Let's check that out. So this distance from here to here is 1.64 centimeters. Is that the object distance for the second lens? Well, no, it's not. The object distance for the second lens is the distance between the second lens and the object that it sees, which is that red arrow. That's not the same as 1.64. In fact, the object distance that the second lens sees has to be 1.64 plus L, which is 2 centimeters. So the actual object distance that the second lens sees is 3.64 centimeters. This is 2 centimeters. So I cannot use 1.64 in my equation here. This is a common mistake and one that I implore you to avoid. This is not the correct number. I have to take into account the distance between the lenses. That will change the distance between the second lens and wherever the first lens creates its image. So what I really need here is 3.64. It's plus. All of our object distances are going to be positive. Down here is the same thing. If I redo my calculation, I'm going to get a number that is plus 2.55. What do I know? I know that this is real because I have a positive there. Certainly is a real image. It's on the opposite side of the lens here as the red arrow. What else do I know? I'll calculate my magnification. Now I can't use this number. It's wrong, so I'm going to put 2.55 centimeters in there. I still have my negative sign out front, so instead of minus 10.7, I have minus 0.71. Well, what does this tell me? This tells me that it is an inverted image. Is that true? Sure is. It's the opposite. E is the opposite direction as the red arrow. And the size, 0.71 of the red arrow, that's a little hard to say. I guess I'd buy that. So now I put these two together. Instead of 10.7 here, I have minus 0.71. And when I do that math, I come up with minus 0.33. This tells me that the final image compared to the initial object is inverted, and it's about a third of the size. So let me check that out. Certainly this is inverted compared to that, and roughly a third of the size. Okay, so far so good. So We just have to be really careful about this switch from image of the first lens to object of the second lens. If mistakes are made, that's one of the places where it's likely to happen. So in this case, our answer here, the mistake is made at C. D seems fine, E seems fine. All right, let's move on. So this is an aside, but it's an aside that will get us to telescopes and microscopes, so it's worth taking. So here's a question. Maybe you've noticed this. Objects that are further away look smaller. Why? Which of these explanations gives you the reason why objects that are further away look smaller? Pause the lecture, take a little time to think about this, and go to the quiz, answer the question, come back, we'll talk. Okay. So, obviously not F. That's not a good answer to the question. Turns out that it's all about the room that things take up on your retina. Your perception of size visually is how much real estate does that object take up when it's projected on your retina. A very large object is large to you because it occupies an enormous area on your retina. It isn't really about dimmer. It's not about brighter. It isn't about virtual real. We'll get into how the eye creates images on the retina next time. It's all about that angle that the image of the object takes up on your retina. Okay, so let's just take an example of that. So here I have an object. The first picture is an object that's somewhat further away. The second picture is an object that's closer. I can see that that first object, let's call this the initial angle it takes up on my eye. When I move it closer to me, it then takes up a larger angle. It looks bigger. So far, so good. What can I say about the angular magnification of that object as it came nearby to me? So we know this. The angle that the object takes up on my retina is related to how large I perceive the object to be. Can I quantify this? I can in something called the angular magnification. And that is a comparison of the angles that this object does take up on my retina. So I'm going to take the final angle divided by the initial angle. So if that angle doubles, I perceive the object to be twice as large as it used to be. Now, here's a little trick. If this angle is small, and most of the time these angles are going to be small, given the size of your pupil, given the sorts of things that human beings look at, the distances we operate on, that angle is almost always a pretty small one. So I can replace these angles by tangents of these angles, and that's going to give me an in. It's going to give me a foothold to be able to rewrite this with some parameters I know. For instance, I'm going to say that this distance between the object in the first picture and your eye, I'm going to call that the initial distance. I'm also going to say the height of the object is some number h. In the second picture, the height of the object actually hasn't changed. It has gotten closer to your eye, so this is the final distance. Those are two sides of a triangle. I can use those to find tangents. So for instance, the tangent of the final angle in this picture is the opposite side over the adjacent side. The tangent of the initial angle, whoops, I wrote initial when I meant to write final. This should be the final. The tangent of the initial angle is going to be h divided by d initial. That is opposite over adjacent. So what do I get out of that? Turns out I can cancel those two h's, same number. I'm going to have d initial on the top because it's in the denominator and a denominator, and d final on the bottom. So actually, the size of something is related to its distance pretty directly. If I bring an object from, say, 100 meters to 50 meters, my perception is that it will have doubled in size as I perceive it. Okay, so that's a useful way to quantify angular magnification, how large things appear based on how much space they take up in your retina. Now, this is going to become important when we talk about magnifying glasses. Let's imagine we're trying to look at an object up close. Now, every eye has something called a near point. That near point is as close as you can bring an object before it starts to get really fuzzy, before you can no longer focus on it. In general, this is a very general thing, near point for a human being is about 25 centimeters. That obviously changes with individual, it changes with age. So it's not at all an absolute constant, although you will find in many equations people will replace the near point by 25 centimeters just as an approximation. We'll see that when we get to microscopes. So again, this near point is the closest you can bring an object before it starts to get really fuzzy. And you can try that for yourself. You can bring an object close to your eye and you can see at what point can you really not focus on it anymore. That's your near point. Near points get larger with age, so my near point is almost certainly further away from my eye than yours. But what would happen if I want to really examine something up close? I want to bring that object close to my eye. The problem is now I can't focus on it anymore. It's too near. The lens in my eye isn't able to bend the light sufficiently to have that object focused on my retina anymore. Okay, so what do I do? Well, that's where I would introduce a magnifying glass. Magnifying glass is going to be a converging lens. I'm going to draw it here. I'm going to kind of pretend that it's really close to my eye. Here's my converging lens, really close to my eye. So I'm ignoring the distance between my eye and the surface of the lens, just to make things a little bit easier. So let me back up for a second. Before I had the lens there, this object was taking up a certain space on my retina. Let me draw that little green object there. So this is kind of the before. When I bring that object closer, it now takes up a different angle, a larger angle. So it appears bigger to me. That's what I want. But again, the problem is it's too close. I can't focus on it. What does the converging lens do? Well, a converging lens can create a virtual object of this thing that's close to my eye that's further away. Right? So I can create this virtual image of the object. It'll still give off this ray. So here I use this magnifying glass. I use this converging lens to create a virtual image of my object that's far enough away that I can actually see it, that I can focus on it. But it takes up a larger angle on my retina. I essentially can bring it close, and I use the lens to move it further away so I can actually focus on it. Bringing it close means I increase the angle that it takes up on my retina. What the magnifying glass does, this converging lens, will create a virtual image far enough away that I can actually focus on the thing. Typically very, very far away. So I can relax my eye and focus on this distant image. All right, a couple of questions. Given this explanation from everything you've heard now about magnifying glasses and how they work, would you say this is true or false? A magnifying glass creates a real image directly on your retina. Pause the lecture, go to the quiz, say what you think. Is this a true or false statement? Okay, let's see. So, we said the magnifying glass creates a virtual image of the object. It does not create a real image. If you created a real image, it would create an image back here somewhere, behind your eye. That doesn't help you see anything. So you are not creating a real image with a magnifying glass. You are looking through the magnifying glass to see the image. We'll talk about this next time. This is how glasses work, or contact lenses. They are not creating real images. You're creating virtual images. You look through these things to see the image actually on the same side as the object, which is the thing that you're trying to look at. So the magnifying glass does not create a real image. It creates a virtual image, which then your eye can focus on. Second question. And I need to erase a little bit here. Where do you want the object to be in relation to the lens of the magnifying glass in order to magnify? So when I use this magnifying glass, where do I want my object? Do I want it very far away from the focal point of this magnifying glass? The object is the thing I'm trying to look at. The object is the thing I'm trying to magnify. This green arrow, do I want it close to the focal point of the magnifying glass, or do I want it much closer to me and to the lens than the focal point of the magnifying glass? Another question. Pause the lecture, go to the quiz, say what you think. Okay, so how do we get through this one? Well, we've got some hints here. First off, we want a virtual image. Again, we don't want an image behind our head somewhere. We want a virtual image that we can look through the magnifying glass and see. Well, anything outside the focal point of a converging lens, and a magnifying glass is a converging lens, is going to create a real image. So we do not want this green arrow to be further away than the focal point of our lens. Otherwise, we're going to get a real image and this isn't going to work. So how do you choose between B and C? Well, here's the thing. I would actually like this virtual image created by the magnifying glass to be as large as possible and as far away as possible, because then I can relax my eye. What's the condition of that? So I'm going to use my handy image distance equation. And here I have a converging lens, so my focal length is always greater than 0. I know that the magnification that this lens will introduce is going to be minus di over do. And if I plug this equation for di into that, I'm going to cancel out a do and just get minus f d naught minus f. Here's the thing. If this denominator gets close to 0, m gets very large. So I want this close to 0. When will that happen? That'll happen if d naught is close to f. So I actually want this object, this green arrow, to be such that it is close to the focal point of my magnifying glass. And I will adjust the position of the glass and my head to make sure that happens. Now, I want it just inside the focal point of the magnifying glass. Because I want to create a virtual image. If it's just outside the focal point of this converging lens, I'm going to get a real image. I don't want that. So it's just inside, really close to. That's how magnifying glasses work. They allow you to bring objects really close by creating images you can actually focus on that are far away. And by bringing those objects close, they take up a greater angle on your retina. All right. Now that we have that down, let's move on to some more complicated optical instruments, namely telescopes and microscopes. All right. So, the reason why it's important to go over magnifying glasses as a prelude to talking about telescopes and microscopes is because both devices have two lenses in them. They have what's called an objective lens and an eyepiece. the eyepiece in both cases functions as a magnifying glass. So in both cases, I hope I'm spelling eyepiece correctly, but probably not, essentially as a magnifying glass. The objective lens will create an image here or here, and you will use the eyepiece as if it were a magnifying glass to look at that image up close. So that's the function of an eyepiece in both a telescope and a microscope. And we can see, you can calculate out the magnification you get from both instruments if you know certain aspects about them. Now, telescopes are actually a little bit simpler. This is just a straightforward angular magnification. Here I'm comparing angles. I can do that through trigonometry, compare these two angles, and get an angular magnification. Microscope is a little bit more complicated. It's actually, I have to have a compound of two magnifications. This is a compound microscope. There's the magnification introduced by the objective, which is that O, and by the eyepiece, that E. And if I want to actually calculate or come up with an expression for the magnification of a microscope, I've got to make some simplifying assumptions. You can kind of see these in the diagram. The nature of them isn't that important. There's certain things you ignore. For instance, you ignore the focal length of the objective lens. It's small enough that we don't care about it. Not that relevant unless we're actually deriving these equations. If you want to do that, you need to understand these. I think more interesting is to think about how these devices function. And how can we use what we have learned about lenses to make some determinations about how they function. So I'm going to move beyond this, and we're going to go to looking at some pictures. So I've got two sets of lenses here. A first lens and a second lens, an objective and an eyepiece. We're assuming the light's going this way, so this is the direction of the propagation of light. Which would mean your eye would be over on the right side. So we're assuming in both devices, your eye's over here looking. Okay, which is usually the way these pictures are drawn. So that's the situation. I want to be able to tell the difference, which of these is a telescope and which of these is a microscope. In particular, which of these is a microscope. That's what I want to know. Which of these pictures shows a microscope? So, think about what you know. Think about what you learned from the pre-lectures, a little bit about what we talked about here. Pause the lecture, go to the quiz, and let me know, A or B, which is the microscope? Well, let's see what we can say. So, let's look at A for a second. So here's the thing. We know that the eyepiece in both devices needs to function like a magnifying glass. And we've already determined the object of that magnifying glass needs to be around the focal point, just inside the focal point of the converging lens. That is the magnifying glass. So in both cases, I'm going to want an image somewhere around there. In order for the eyepiece to function properly, just like a magnifying glass, I need an object. It's the image of the first lens. How do we write this? This is where things get complicated because images and objects start to blend together when you're dealing with multiple lenses. So this is the image of the first lens, which then becomes the object for my eyepiece. That's a little messy. Let me try to clean that up. In fact, I'm going to just rewrite that whole thing. So the image of my first lens needs to be close to the focal point of the eyepiece in order for the eyepiece to function as a magnifying glass. In which of these cases can that happen? Well, what am I doing with a microscope? I'm looking at something that's relatively close. So in case A, if I had an object, say a bacteria or something right here. So here is my item that I'm trying to magnify. Well, first off, we're in a little bit of trouble because we're well within the focal length of our objective lens. So I'm not going to get a real image. I'm going to get a virtual image. I'm actually going to get something further away than the actual thing. Microscope wouldn't work that well if, in order to look at a bacteria, I create an image that's further away from me than the actual bacteria. You're not going to see it. So A is starting to look like a pretty bad microscope. In fact, it's not. A is a telescope. A is designed for looking at very, very distant objects, objects where the rays are coming in almost parallel to the principal axis of the objective lens. Distant objects look as if the wavefronts are these lines like this. These rays are coming in and will be focused close to the focal point of the objective lens. That's right here. So, if the object's far away, I will create an image in this region where I need it to be so that the eyepiece can function as a magnifying glass. Case B, that's our microscope, right? In case B, now I'm looking at a very small object that's very close. I would need it actually just outside. Let me redraw this. It needs to be just outside because I need a real image. Just outside the focal point of this objective lens. What I'm going to do is create a very large real image. And I position the barrel of the microscope. So this is kind of the barrel of the microscope, such that that image created by the objective is just inside the focal point of the eyepiece. So now I've magnified it once. I'm going to use the eyepiece to magnify it again. So B is my microscope. I can use my image distance equation just to confirm all of this. Again, if the object distance is close to the focal point, then this will be small and this will be large. And since the magnification is minus the image distance over the object distance, if this is large, this will be large, which is what I want. I want to take my bacteria and I want to make it big. Okay, so far so good. So, there are some crucial differences between telescopes and microscopes. And let's actually explore those a little bit. We see the pictures don't look the same. So let me ask you this question. What is the purpose of an objective lens in a microscope? So give some thought to that. Pause the lecture, look at these options, and answer the question of the quiz. What is the purpose of an objective lens in a microscope? Okay. Well, we kind of got to it already, right? So I'm going to back up to the picture that we had. The purpose of this objective lens is to take a very small object that's close and make it very large. So I want to create a larger real image. So I want to magnify that bacteria. I want the image to be real so that I can then examine it with my eyepiece like I would with a magnifying glass. It's certainly a small nearby object that will then, I can use the eyepiece to magnify this image. So the purpose of an objective lens in a microscope is actually to magnify. That's why it's there. And that's why a compound microscope is actually more effective than a magnifying glass. If you just use a magnifying glass, yes, you can magnify the image of something. But what a compound microscope does is it magnifies twice. The objective is making a larger image of your object, and your magnifying glass, your eyepiece, is making a larger image of that image. That compound magnification allows you to make things much larger when you look at them. All right, what about a telescope? What is the purpose of an objective lens in a telescope? Another question. Pause the lecture, look at these options, think about it a little bit. Telescopes are actually in this way a little trickier than microscopes. And go to the quiz, select which one of these you think is correct. All right, so what do we want an objective lens in a microscope to do? Well, we can go through these. Actually, start from the bottom up. First off, we need our objective lens in both telescopes and microscopes to create a real image because it needs to be near the eyepiece. We don't want our objective lens to create a virtual image. That would be on the same side of the lens as the object. That's actually further away from us. So we don't want to create a virtual image. We want to create a real image. We also, and here's the thing about telescopes, that objective lens is not designed to create a larger image of the thing you're looking at. Like, let's say you're taking a telescope and you're looking at the moon. The image created by the eyepiece, by the objective lens, is not larger than the actual moon. There'd be no way, right? You can't do that. It would be useless to you. What the objective lens does is not magnify the image that's out there. You're looking at a star very far away. You're not creating an image that's actually bigger than the actual star. That's not what the objective lens is there for. Very different function than in a microscope. In fact, and this may be counterintuitive, the objective lens in a telescope is actually there to create a smaller image of the object you're looking at. But, and here's the big but, closer. That's the problem with these objects like the moon. They're far away. So what the objective lens in the telescope is designed to do is mitigate that, bring it close. Just like the objective lens in a microscope takes a small object, makes it large. Because that's the problem. The objects are small. Telescope takes a distant object, makes it close. So I'm going to create a tiny, tiny, tiny image of the moon, much, much smaller than the actual moon. And then I'm going to examine that with my eyepiece. But it's close, so that I can actually get quite a bit of detail out of that. So the objective lens in a telescope, it has a unique function, very different than what you would expect out of the objective lens in a microscope, because they're looking at different kinds of objects. Okay. One last thing. Yes, and this is the point I made. You are not, in an objective lens in a telescope is not creating a larger image of the moon than the moon itself. All right, so let's just look at these two expressions for magnification for telescopes and microscopes and pick out which statement do we think is true. So we've talked about these things a little bit now. You should have some experience, feel some stirrings of confidence, I hope. Which of these statements is true? Pause the lecture, go to the quiz, and let me know what you think. Okay, so let's see. So we're interested in what kind of lenses do we want in microscopes and telescopes. Now this term powerful, I used it last time briefly when we were talking about lenses. I do want to just reemphasize, a strong lens, a powerful lens is one with a very short focal length. It can bend light really effectively. A weak lens is one where the focal length is quite long. It isn't really able to bend light very well. Okay, so what can we say? Do we want a powerful objective lens in both microscope and telescope? Well, that would mean a very small, so this would be f naught small, or FO. It's not an f naught, it's an FO for objective. In both, that actually works okay here. Doesn't work so well here, right? I don't want a small objective focal length because that gives me a small magnification, so I don't want that. How about B? Powerful objective lens in a telescope, which means a small FO. Weak objective, large FO. That's exactly the opposite of what I want. A large objective focal length in a microscope, because FO here is on the bottom, is going to not be good. It's going to make a small magnification. Same thing, same problem we just ran into with the telescope. A small FO is going to give me a small magnification, so B's out. C, well, C looks like it might be right. I actually want a weak lens as the objective lens in my telescope. That means I want a small focal length. Sorry, I'm confusing myself. I want a large focal length. A weak lens is one where it takes a long time, a long distance for those rays that are coming in parallel to the principal axis to be converged to a point. So a weak lens means a large FO. That actually works, right? A large FO here means a large magnification. And for a microscope, a powerful objective lens, a really powerful lens, bends light a lot. That light will converge quickly, so I have a small FO. Small FO kind of works here. Small number in a denominator means a large number over a large fraction. And yeah, D doesn't work. So C is the one I want, which is, again, maybe counterintuitive. That you actually want a very weak, the weaker objective lens you have in a telescope, the better off you are. Why? This will be explored in discussion a little bit. There's one question in the discussion packet that does address this. So I encourage you to practice with the discussion sheet, get some good experience here, and I think you'll find some confidence in thinking about this stuff. So I will say goodbye to you now and see you next time.